cyanide as a nucleophile. We also saw how aldehydes and ketones can be converted into cyanohydrins by using a combination of, basically you need HCN. Basically we need HCN, but the mechanism, if you think about it, you protonate and the nucleophile attacks. But more commonly, we take cyanide with H plus instead, so because HCN we don't want to keep stored. And then the other one we saw, which is a new method, is from a primary amide. From a primary amide, using a drying thionyl chloride, which is actually going to be a dehydrating agent. It's taking H2O out. Isn't that right?
Yep.
Of these, I think the mechanism that we really need to know is SN2, because we've done SN2 like to death, so we should know. Then reactions of cyanide, a couple of them that we've seen already is nitriles can be hydrolyzed either under acidic conditions or under basic conditions. But then you have to protonate again, convert into carboxylic acid. That's actually a very common way of making a carboxylic acid is by hydrolyzing a nitrile. Or nitriles can be reduced with lithium aluminum hydride, where the CN becomes a CH2NH2. We've seen those. And the last one, which is a new one, and that is reacting with one equivalent of the Grignard, okay, R prime, and converts this into a ketone. That's the last thing I think we wrote.
Yep.
Okay. Now, of these reactions of nitriles, we will discuss. Are we going to discuss the mechanism? We will definitely go over the mechanism for this one, definitely. I'm trying to remember, are we going to go over the mechanism for that one, or is it okay to skip it? We'll see. I think it might be skippable.
You said something about that we could go over the mechanism from
Okay.
turning nitriles to carboxylic
Okay.
acids.
Okay, so let's start looking at these and then we'll write mechanisms and stuff. So please tell me. What will be the product please tell me
The ethyl group replaces the nitrogen, and the C is double bonded to an O.
So do you, okay, and maybe we don't know how to name that. Well, we do kinda, right? Oops, not benzene, what do you
cyclohexyl.
One cyclohexyl, one propanone or propane one one.
Yeah.
Is that what everybody is thinking?
Yeah.
Is that a yes or a no?
Yeah.
Okay, let's write a mechanism. Let's see how that is happening step by step by step. So what do you think will be the first step?
Grignard.
Because there's no acid. So Grignard, what about the Grignard? Okay, where would the Grignard attack?
The carbon?
Because that's the electrophilic position, which means just like a ketone, just like an aldehyde, except now you have a nitrogen, but everything else is exactly the same. So what does that create? Excuse me. That creates ethyl goes here and minus. Agreed? Agreed? What next? Is there a leaving group? Can this negative charge fall back and kick out a leaving group? Maybe kick this out, or maybe kick that out. No, those are bad leaving groups. So, by
That's
the
a
way,
good
the
base.
mechanisms are very similar to the ones you've seen for aldehydes, ketones. So think about it. What should be the next step?
The nitrogen gets protonated.
That's when the nitrogen gets protonated. So the first step finishes right there. The Grignard step is done. There's nothing more for it to do. So that's when we then add hydronium. So nitrogen gets protonated, makes, you've seen this before. Can someone tell me what is this family of compounds called?
An amine.
That's an imine.
Imine.
It's a double bond. Imine.
Imine.
Okay. Next step. Thoughts? Next step. Louder? What will H2O do?
No.
No, go ahead, think about it. What do you want H2O to do? Is H2O an acid to give a proton? Unless you had a strong base. See, water is a weak acid, weak base. It will only react with a strong counterpart. Is there a strong acid, no, not really.
No.
Yes.
Would it attack the ferment?
So, is that what you're thinking, Annika? So act as a what? What is it acting as if it's attacked? Nucleophile. So let's pause here because we got to think about this. I see this. Let's critically analyze this. So if or water were to obviously not act as an acid because it's weak and there's no strong base. But okay, what if this acted as a nucleophile? What will that create? What will that do to the N? What did you say diluted?
No.
Is that what I heard?
No.
What will happen to the N? Will it? There's a double bond. It won't be kicked out. So what will happen, guys? You guys are going too deep right now. What will happen to the N? It'll become a
Negative.
negative. I couldn't hear that. I'm just old. I'm hard of hearing. You guys like, just say it again. Negative. So here's my question, and that's why I want you to pause. Which reaction is faster? Nucleophile, electrophile, or acid base?
Acid.
Right?
Acid base.
Everybody agrees? This
Yeah.
is something you got to remember. Acid base reaction is faster than nucleophile, electrophile. This is the end of step 1. This is where step 2 is happening. Is there acid in this system?
No. Yes.
Where? You said no, you said yes. Where?
The H2.
Are we just adding one H3O or are we just dumping in 10 milliliters, 5 milliliters or whatever it is?
25 minutes.
Whatever, right?
Multiple.
So multiple, many. So just because one got used, can another not be used again?
Yes.
Yeah.
There are plenty. But is there a base? Is hydronium a strong acid or a strong, I was going to say strong base. Do you consider H3O plus to be a strong acid? Strong, not dilute. Dilute concentrated is different from strong weak. Totally different thing. Dilution concentration is about the number of moles per liter per milliliter, whatever. Strength is about pKa's. So is H plus considered a strong acid, strong base? Pause.
Well, H2O is
Pause.
weak.
I didn't say H2O. I
Yeah,
said
no,
H
but I'm
plus.
trying to analyze.
Is this a strong acid, is this a strong or a weak acid in general? Again, we're not comparing. In general, when you see hydrochloric acid, do you think strong or weak?
Strong.
What's the actual acid?
H plus.
Is this considered a strong acid or or a weak acid in general? Again, we're not talking specifics here.
Strong.
What's the actual acid?
H plus.
Is this, I think you're getting my point.
H plus. H plus.
It's H plus.
Strong acid.
Acid. That's what acid
Strong
is
acid.
an H plus. And hydronium, of course, is H plus mixed with water because it's dilute, but H plus. So, is H plus a strong acid or a weak acid?
H2O
Strong
plus is strong.
acid.
With me?
Yes.
Yeah.
Is there a weak base?
The
NH.
NH.
Right there.
NH.
Why the pause?
Bec-
Why the because
A lone
it's the
pair.
same thing. Oxygen with lone pair can take a proton from H plus hydronium. Why can't NH with a lone pair take proton from hydronium? Isn't it the same thing?
Yes.
The
Yep.
point I'm trying to make is, which is why I asked you to pause, is if there is an acid in the system, protonation must happen first. Nucleophile attacks after. You cannot attack the nucleophile first if there is an acid in the system. That's why. So the point is, this is the place where we are going to protonate first, because there is acid. There's acid all around us. So when you protonate it, just like aldehydes, ketones, that makes this even more electrophilic, so that now the nucleophile can come in. Please remember, if there's an acid, protonate first, then nucleophile. If there is no acid, like here, there was no acid, that's why we do nucleophilic attack. Make sense, everybody?
Yes.
Please remember that. Okay, oh shoot, sorry, no, okay. What's the next step then? Now comes the nucleophile. Where is the nucleophile going to go? You're absolutely right, the nucleophile will go to the carbon. Absolutely right. But protonate first because there's acid here. And then that creates did you say an alcohol?
Oh, I know.
I don't think you
I'm not used to today.
agreed. What do you think that needs to do?
Get rid of a proton.
Okay, good. That needs to get rid of a proton and okay, let's do it one step at a time. That's fine. Okay, so if that gets rid of
It's-
a proton,
Yeah. Give and take.
huh? What?
A proton.
What?
Mar said give it.
Exchange of protons.
Where? Okay, good. So where this gave a proton, who's taking a proton?
NH2.
You can either show it in one single step or you can, but not from each other. It's not like this nitrogen taking that proton. It's not intramolecular, it's intermolecular. Proton gone, proton accepted, but from different sources. So that's totally up to you, absolutely. So yes, there is a proton exchange. Now what? Exactly. Now you have a good leaving group. What is the leaving group going to do?
Leave.
It leaves.
If it leaves, what does it leave behind?
A carbocation.
What is so special about this carbocation?
Resonance stabilized.
So what is the resonance structure of this carbocation?
Okay. See.
The
Alpha.
double OH plus.
What is that?
I mean, CO.
The a lone pair goes from the oxygen and makes
Got
another
that.
bond.
What is this?
Cycle.
I'm not asking for the name. I don't think we need to do that. But what is this?
The resonance structure.
Okay. What is that?
A ketone.
So what is this?
A key.
Ketone with an extra proton.
A protonated
It's a
ketone.
protonated ketone. Perfect. So what does the protonated ketone need to do to become a
Deprotonate.
ketone? It
Gets
just
rid of a
needs to
proton.
Get rid of a proton and become what you're looking for. Done. Again, please notice, guys, the mechanisms are very similar to the ones you've seen before in aldehydes and ketones in terms of the logic. If there is no acid in the system, nucleophile attacks. And protonate in this case. But then if there's an acid in the system, you got to protonate first, and then the nucleophile attacks, kicks out, makes a resonance stabilized carbocation, and blah blah. Very, very similar. Do you guys see that? Now, is there any way you can get an alcohol from the nitrile reacting with the grignard? Is it any possible way, if you think of the mechanism in front of you, and let's say, here's the mechanism, and here we say, oh, we get an OH. Is that possible?
Yes.
Tell me how.
Toto. No.
Where? How?
When-
Tell me how. Where?
Carbon, the carbon.
Where is an alcohol?
Well, in H3O plus, right?
So tell me how. What mechanistically, how would I get that alcohol in this mechanism?
Will it be MCPVA?
Okay, I'm not asking for a different reaction.
No.
I'm saying in this reaction, is that product possible? For this reaction, is that product even possible?
No.
Looking at the mechanism.
Some of you
now.
might think that can't the Grignard attack again and give us the alcohol? The answer is absolutely not. Why? Because as soon as you added that guy, as soon as you added this guy, what happened to Grignard?
It got pronated.
So does it matter if I took excess of Grignard? Can I then get the, maybe then I can get this as the product, right? Is that possible? No. Why not? Doesn't matter how much Grignard you took, because as soon as you added dilute acid, what happens to Grignard?
It's
Gone.
gone.
It doesn't exist. It's destroyed. So the point is, you got to think about those details. That hey, is this even possible? What is the H3O plus doing to the Grignard? Oh, there's excess, so don't get tempted. Doesn't matter. You guys seeing that? Everybody. Cool. Go ahead. Let's try it one more time. And you guys go ahead and write a mechanism. Where did I put my Please tell me what's the product.
Benzoic acid.
You all agree? Everybody okay?
Yes.
Yep.
Let's write a mechanism. Let's try and understand how is this being created. Step number one. What would you say for step number one? Now, please.
The nitrogen gets
You
pronated.
have to, because there's an acid. If there's an acid, you got to think about it. Can something be protonated? Because acid-base reactions are faster than nucleophile electrophile reactions. Okay, then what? The nitrogen is protonated. Now what? After protonation, what happens? I'm hearing mumbles. Just could we say it louder?
Okay.
With the O, water attack.
Water, what?
With water attack the
Carbon? So nucleophilic attack? I think that's what Anika was trying to say also, but couldn't hear it. Agreed?
Yep.
Protonate first because there's an acid, then nucleophile attack. If there's no acid, nucleophile attack first, then protonation. Exactly. So attacks, what does that create? What would you do next?
terminate the NH.
Before that?
Proton exchange.
Oh.
So the point is, this has to give a proton, this will take a proton. Agreed? Everybody? So a proton exchange, so that, okay, next step. Next step.
Then we coordinate the NH2.
You can't protonate when it already has a plus sign.
What's the delete?
Not yet, because there's a double bond.
Huh?
So think about the product.
Oh, yeah.
So are we adding an OH?
I think we need to.
Water. Nucleophile.
We're adding water. Because it has 2 oxygens, not 1.
What would that create? Not yet. Exactly.
Another proton.
Then proton exchange, which causes, of course, these are all reversible steps, but that, okay. What will you do next?
It's a
And H3 is a good leaving group.
living group.
Okay, so what will you do next?
Carbocation.
What will needs to happen for that to happen?
The leaving group leaves,
Okay.
resonance, stabilized carbocation.
Leaving group leaves to create a resonance stabilized carbocation,
Mhm.
right? The leaving group has to leave to create that carbocation.
But
Would it be okay with you guys if I just did this? I'm just jumping to the resonance structure. It's a resonance structure. Resonance structures don't exist. What exists is the hybrid. So whether you show this resonance structure or that resonance, that's our choice. A lot of people just do that. Okay, what next?
The double bonded O and C is that proton.
This is the mechanism for acid catalyzed hydrolysis, not hydration, excuse me, hydrolysis of a nitrile. But again, please look at the similarities here. If there's an acid, you got to protonate first, then nucleophilic attack. What about in the absence of an acid?
The nucleophile attacks.
Exactly. That's the only difference. Everything else, the pattern is the same product. So if you're writing a mechanism for that, what would you do first in this case?
Take.
Same?
No. OH.
There's no acid.
No acid.
Attack.
That comes later. First step, there's no acid. So we can't protonate. So therefore, what should happen first? Nucleophile attack.
The hydroxide attacks.
That's right. Once you attack a nucleophile, and then it takes a proton. Now, who is it going to take a proton from? The reason also I stopped you earlier, Anika, and this is something also everybody has to think about. When you are doing reactions in an acidic environment, please notice the 2 mechanisms that are in front of you on those 2 boards. Those are both happening with acids around. Can we write any structure with a negative charge? Can a negative charge exist when there is acid around?
No.
Not possible after this, because that's when the acid came along. It's not correct to do so. There can be no anionic intermediate if it's in an acidic environment, not possible. But at the same time, when you're doing things in a non-acidic environment, when there is no acid involved, then you can't have a positive. You have to have a negative, electron-rich thing. So those are things you got to also keep track of. What will this do next? Suggestion.
Protonate the.
And where is that proton going to come from?
H3O plus.
Water.
The second step.
Water, exactly. No, we haven't added that yet.
Oh.
This is still happening first step so far. Because the first step is going to give you the carboxylate. It's the second step that puts a proton back on it and creates the carboxylate. So the H2O plus is not there right now. But what is there in addition to hydroxide?
Water.
Because hydroxide has to be dissolved in the water, aqueous, it's always aqueous. Exactly, so that takes a proton. What does that become? Right? And what does water become?
A hydroxide.
So what should be the next step?
Okay.
And if you have like a track.
Who's
Attacking.
attacking?
Oh,
Hydroxide.
Another attack by hydroxide.
And what's the next step?
water again to protonate the NH.
Do you want to see that? Everybody okay? Okay, what's next? You can't have anything positive when you're doing reactions in basic environments, just like you cannot have anything negative in an acidic environment. So what do you think should happen next?
Do you have water again?
Where will the
You-
water go?
You make a leaving group,
Which is a good leaving group?
NH2 or OA, either one.
Well, OH we don't want because that just takes us back,
Yeah.
right?
So
if you
NH2.
go forward, it's either R or NH2.
NH2.
right? Not R because we want to keep it, so NH2, okay.
Will we do that thing where?
But then that leaves a carbocation, positive. Say again? Where will that, oh, you're saying that will, make this? I don't think so.
How about a hydroxide attacks the end? I don't know.
Hydroxide attacks the what?
The end, the nitrogen, the amine.
But, that already has an octet.
Yeah.
Why would hydroxide attack something that is already electron rich?
To make it a leaving group?
How can minus go to a minus?
Oh, no.
Electron rich doesn't go to electron rich. Electron rich goes to electron poor.
But shouldn't we make it a leaving, good leaving?
we need to somehow kick it out. You're absolutely right. So here is where hydroxide comes in again, but not as a nucleophile, as a if
Oh.
not a nucleophile, what?
An electrophile?
A base.
A base.
Something that's electron rich can either be a nucleophile or be a base.
A
Those
base.
are the only two things an electron rich thing can do, either go for a proton or go for a electrophile. If this cannot go as an electrophile because there's no, cannot go as a nucleophile because there's no place to attack, can it take a proton? Yes, it
Yeah,
is a
it can take a
base.
proton.
Takes a proton. What does that become?
Oh, alkoxide, or, not really.
I agree with what you're thinking.
but not, it's
And
not
that's
called out.
okay, we don't have to give it a name, that's okay, we don't have to give it a name. But what you're thinking is O minus, right? I would not call it an alkoxide because of everything else that's on it.
Okay,
But that's what you're thinking, right?
that's right.
Yep.
What next?
Oh,
The electrons.
Electrons from the O form a second bond and kick out the NH2.
That's how the group gets kicked out. You cannot make that NH3 plus because everything is in base. Can't do that. But now you can kick it out as NH2 minus, it's gone, and leaves behind, what do you think next?
Oxygen.
So why do we need the second step? Didn't we already get the carboxylic acid?
To neutralize the NH.
Who cares?
When you don't need it.
But we do. Please think about this, guys. I'm going to ask you this. What do we call this compound? I'm going to erase this just because it's crowding things too much. What family is this compound?
Carboxylic acid.
Please say that again.
Carboxylic acid.
One more time.
Carboxylic.
Acid. Acid. What is hydroxide?
A base.
So can this exist?
No.
Can this
No.
exist as long as there is hydroxide floating around? Can I get carboxylic acid?
No.
No.
Not in basic conditions.
Exactly. So as soon as that is created, you can't stop it because that's going to automatically do an acid-base reaction, take a proton. This is where the step number 1 ends.
oh,
Carboxylate. Now it's done. It stops. So this is where, of course, there's NH2 minus floating around also. It's just that I don't really care about it. This is where hydronium comes in to protonate that guy. Because we lost the proton, so we need to put it back.
And it stabilizes right there.
So the mechanisms for the two reactions here that one is the reaction with Grignard, and the other is acid and base hydrolysis of nitrile to give carboxylic acids are on the board. So please practice them. Please make sure you've got the sequences right. Never make a negative anion in an acidic environment, and never make a positive ion in a basic environment, not possible. Okay, let's try a couple more. Let's do these fast, guys.
Nitrile. NBS. Easy bromide. Turns it into a ketone.
I think you lost a carbon. I don't know who did this one.
That was me.
Let me see. Yeah, I
One,
think you
two,
lost a
three.
carbon. Think of it, so let's think, right, 7, 1, 2, 3, 4, 5, 6, 7, 8,
Eight.
and then 2 here,
Oh,
lost a carbon.
that's right.
Oh.
Sodium cyanide.
Yeah, keep track of your carbons, please. Yeah. Yeah.
Okay.
Ooh, no. No, I think you're thinking NBS. HBr adds across the double bond. It adds. Yeah.
Attacks, doesn't it? Did you get it?
I can see it.
HBr goes across the double bond.
So are these connected?
Yeah,
Yeah.
they're all together.
This is
So
all
this goes forward, yeah.
Oh, okay.
Well,
Oh, okay.
so just do,
Were you
Greener.
saying something, Anna?
Oh, no, sorry.
No, don't be, I was just wondering if your hand was up.
This is possible? Having H2O plus here and then adding. Oh.
yeah, because you finish one. You finish,
What happened?
I'm not, I feel like I'm scared because I'm like, is
Yeah.
this possible? Wouldn't,
No, they're separate.
they're separate.
So
Okay.
as I think Mara is saying, this is finished, you
Oh,
got
you used
whatever
it,
you
okay.
got from here, then you did this, then you did this.
Oh.
So that's why they're numbered, they're not together,
No.
they're separate reactions.
no, but,
Oh,
but that's continuous.
I think the first 3 step.
You have to do all the way to 5. Oh, you did it.
Oh,
Oh,
I
you did
see.
it, okay.
But no,
No?
The first,
not not the product.
the first 3 steps give you a carboxylic acid, that's for sure.
1, 2, 3 carbons. You need 1, 2, 3. Yeah, you have the carbons, right? 1, 2, 3, 4.
People throwing stuff around now.
I flip my stuff around, it does that.
I thought you had it right. Oh, because
I'm confused. It's an excess.
but it's an MGBR.
What do you have, Camilla, what do you have after step 3? What's the product after step 3? So carboxylic acid.
Mhm.
What do carboxylic acids do with excess Grignard? What do you get? Anybody? And this is a question for everybody. anybody?
A ketone?
A ketone. Again, mechanism, so the hydrate that you drew earlier can't survive. It dilute acid farther and becomes a ketone at the end. So everyone should know the mechanism of those steps. And actually, we've written it in the quiz and the exam also once. Ketone. You don't have to write the mechanism, it's okay, you're not into mechanisms. And then, what next? Oh, you don't have to, anybody can, unless you can.
I'll try.
Well, we're adding a C.
1, 2, 3, 4, 5, 6, 7. I missed 1, 2, 3, 4, 5, 6. Missing a carbon. A ketone reacting with cyanide and H plus.
Yeah, why did you erase those? It'd be nice to erase.
It was kind of messy, I couldn't quite hold it
Ketone.
together.
Anybody?
A
want to
nitrile.
take this forward?
Nitrile.
But let's do it faster, please. But then where's the oxygen?
We took out an equivalent of H2O.
No, not
Mm-mm.
here.
Oh, not there. Okay.
Mm.
Oh.
Guys, please, yeah, go ahead. No, ketones reacting with cyanide in presence of an acid. What does that give us?
A nitrile.
But not an, I think I see where you're coming
Oh.
from, but it's not just any nitrile.
Cyanohydrin.
It's a
that's right.
cyanohydrin nitrile. Exactly. It's a cyanohydrin nitrile. That's not a cyanohydrin.
Oh, so we just take out the R group.
No,
I'm trying
No.
to remember it.
so cyanohydrin is where the proton goes to the oxygen and the nitrile goes there. That's it, you're done.
Okay.
So what is that? Yep, that's a
Okay, now
cyanohydrin.
that makes sense.
That's you're adding HCN across the pi bond. You're basically adding HCN across the C double bond O pi bond. Good, that's cyanohydrin. Okay, next.
One, two, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7.
Go ahead, Mark, you can help.
No, I think she's doing
Yeah,
what I'm doing.
Yeah, yeah, help.
You can also go, and that's okay. Carter got us to that point, maybe we can take it forward and take to the next step. Here, oh, I have some.
You wanna
Yeah.
stay? Oh, okay.
Well, I don't do it this way.
While these guys are figuring this stuff out, do you all agree to those? Do those make sense, everyone, while they're figuring that out?
1, 2,
Is this
3,
okay? Everybody?
Yes.
Please note,
5,
this
6,
carbon
7.
is not carbon. Everybody okay? Count your carbons. Do you all agree with the carboxylic acid? Once again, that's the
Yes.
nitrile carbon. Great. Everybody okay with this?
Yes.
Questions? So that's brominating in the benzylic position. That does an SN2 and puts a cyanide here. Everybody, and then
That turns
makes
into
a carboxylic acid, makes a ketone. Everyone okay? Questions? Again, you guys got to know the mechanism of this step. Everyone needs to know the mechanism of this step. Everyone needs to know the mechanism of that step. This, of course, is SN2.
Wait, so you said,
Okay, this one, that's adding across, that's adding across the pi bond. So H goes one place, it's symmetrical, so it doesn't matter which side you do. Then we are doing a substitution, SN2 reaction converts this into a nitrile. Everybody okay?
Yeah.
The nitrile then reacts with Grignard. What does that create? We did the mechanism of that as well. What does that create?
A carboxylate.
No.
A ketone.
A ketone. A ketone.
And then MCPBA turned it into an ester.
That's the Bayer-Villicher oxidation. There's preference to the more substituted side than the less substituted side, so that gives you the ester. Everybody okay?
Yeah.
Now, okay, hopefully they will have figured it out soon.
I'm not sure about mine.
Not quite.
I was gonna do,
Oh, sorry, I was talking to Mark.
Oh.
No, it's a ketone. I mean, nitriles react to give a ketone. Okay, let's go over those quickly. Let's go over the answers quickly, guys. So, do you all agree at least with this part?
yes.
Yeah.
Everybody okay till this part?
Yes.
Everybody okay till this part?
Yes.
Yeah.
We've written a mechanism for that, we've written a mechanism for this, so everyone should be able to write it. Now let's talk about, so, may I just write this a little differently? So that
Yeah.
I'm going to put C here and there. So, that's hydrolysis of what? Of the nitrile or the alcohol?
The nitrile.
So what does the nitrile become?
A carboxylic acid.
1, 2, 3, 4, 5, 6, 7. What happens to the alcohol?
4, 5, 6, 7.
What happens to the OH? Nothing.
Nothing.
Nothing. What happens to the CN?
Carboxyl.
It's carboxylated. So it's just like a hydroxycarboxylic
Done. Don't
acid.
overcomplicate things. Done. It's the CN that becomes a carboxylic acid. Everything is the same.
Mm.
Everybody okay?
Yeah.
Here's reduction of who? Reduction of the nitrile. It's the nitrile that reduces into CH2, NH2. Everything else remains the same.
Yep.
Everybody okay? Now let's talk about the last one. Which group is reacting? Is it the nitrile reacting or the alcohol reacting? Nitrile, exactly. Everything else remains the same. So let me just 1, 2, 3, 4, 5, 6,
1, 2, 3, 4,
7.
5, 6, 7.
Everything else remains the same. What does nitrile become with the Grignard? So that carbon is where the ketone is going to be.
A hydroxy ketone.
That part becomes a ketone, everything else stays the same.
Oh.
Okay.
Nitrile becomes a ketone, everything else stays
That
the same.
clarifies
Although there's
things.
a problem with that reaction, but that's okay, we'll ignore that problem.
What problem?
No problem, no problem at all.
So
But-
mira. No, I'm just kidding.
Okay, great.
I'm just
You
kidding.
tell me what my mistake is there.
Where?
I've made a big mistake in that reaction. No, actually, no, you need only one. Because it only reacts once. I could take excess, but I would still need only one.
Take the hydrogen from the
Ex-
alcohol first?
Exactly, exactly. Not hydrogen though,
Proton.
As we've said like 1,000 times now, you can't have Grignard with anything that has proton in it. And yet I have an alcohol with Grignard, how is that even?
What if you use the excess then? What is it?
I don't know the answer to that.
All
I
the
don't think
Grignard-
that's been, as far as I know, it is not, but again, I have not been keeping up to date with research, so who knows. But that's, the way I've written it, that's definitely a problem.
Yeah.
Yeah. Okay, let's go on, guys. So, this is nitriles. Let's look at the other families of acid derivatives. Can you quickly remind me the main families of acid derivatives? Which ones are those?
One of them is
No, let's
esters.
start from the
With
Y
that,
is equal to, let's start from the most reactive.
Acid
Halide,
Acid
or
halide.
then comes
Anhydrous.
anhydride, not anhydrous, anhydride. Then comes amides. Again, primary, secondary, tertiary, whatever. So those are the four main categories of acid derivatives. I have written them in order of reactivity. Which is most reactive, which is least reactive, anybody?
Acid halides are most, and amides are
Least, right?
least.
So these are most reactive to least reactive. Everybody remembers that? Okay, now, what you will see in the reactions we see for all of these different families of compounds, you'll see a lot of similarities, A common mechanism you will see for these reactions is that a nucleophile will come and attack. Where would the nucleophile attack?
The electrophilic carbon.
Do you all agree?
I do.
Right? They will all make what we have known to recognize as a tetrahedral intermediate. We've seen this before, right? Aldehyde, Grignard attacks, makes a tetrahedral intermediate ketone, blah, blah. We've seen it 20,000 times now.
Wait,
So,
that all?
Sorry, thank you. Yes. Make a tetrahedral intermediate. Now, this is where aldehyde ketones are different from these guys. There is something that aldehydes ketones don't have, which these guys do have. Can someone tell me, read my mind and tell me what am I thinking about?
OH.
Wait,
There is something that aldehydes ketones don't have, so that is where it stops.
Aldehyde ketones.
But
Yeah.
these acid derivatives do have a leaving group.
A leaving group. Okay.
Exactly. Till here, aldehydes ketones are exactly like these guys. But this is where they differentiate because aldehydes ketones don't have a leaving group, so it stops, the O gets protonated, blah, 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 done. But here it doesn't stop. There is a leaving group. Leaving group gets kicked out. And in fact, we've seen this a while ago, so you may not remember it. But then what will this do? What will this create? Anybody? What will this?
A negative, an anion?
An acyl.
Y minus whatever. What? Agreed?
Yes.
Cool. Now,
Oh.
if you start from the beginning to the end, what kind of a reaction is it? Is it addition, elimination, substitution, rearrangement, what? It's a substitution reaction. But is it SN1?
No.
Is it SN1? I love some of you guys' interest level right now. Let's do this together, guys. We've done this 20,000 times. Is this SN1?
SN1, that would.
Why? Because SN1 has to be on an sp3 hybridized carbon and it must go through carbocation.
Yes.
Uh-huh.
So it's not SN1.
No.
This is
Is
an
it
S.
SN2? No.
No, not
Is
necessarily.
it SNAR?
No.
Because it's not an aromatic. So what is this?
Something new that we don't
Good.
know. That we're
I
gonna
like
learn.
that, something. It's nucleophilic because nucleophile is coming in acyl substitution. It's on the acyl carbon. This is the acyl carbon. Nucleophilic acyl substitution, and that's the common thing you will see constantly through all of these reactions, that the nucleophile will attack, whether the O is protonated or not, but the nucleophile will attack, make a tetrahedral intermediate that will kick out the leaving group, giving us a substitution product. So that's the common theme we will see throughout this rest of this chapter. The other thing I wanted to also remind everybody, because okay. Some of other relationships that we might want to take note of. The reason why these are called acid derivatives are because the acid can be used to make all of them.
All of
We
these.
will look at them, look at those reactions. Sorry, what were you saying, Carter?
All of these derivatives come from the acid.
The other thing we will also see is they can all go back to the acid, hydrolyzed back. We will look at those as well. And their mechanisms are going to be extremely similar, following this general pattern. So we'll look at those also. Once you've seen one, you've kind of sort of seen all of them. Then we also said, within each other, the more reactive can be converted to the less reactive, but not the other way around. Right? So we will also see how acid halide can go here, can go there, can also go there, because it's the most reactive of all.
Can it go directly or step by step?
Directly. We'll look at each of those. We'll also see then therefore as this can go here, and it can go here, and ester can go there, but not to the more reactive side. So those are some common things you will see in all of these reactions, and again, once you know one, you will kind of be able to predict all the others. Is that okay, everybody? Yes, so let's start with acid halide, because that's the most reactive family of the four. Let's start with those and then go down the list one at a time. So once again, acid halides are compounds that have halogens on the acyl carbon. How do we make them? How do we make them? There are two ways of making them depending on whether you want a chlorine or a bromine. But they both use carboxylic acids. The only way to make them is from carboxylic acid. We'll either use SOCl2 where the halogen is Cl, or use PBr3 where the halogen is Br. And it's a very fast reaction. It's
PBr3, right?
PBr3, so sorry, thank you, PBr3. Very, very fast reaction. What about the reactions of acid chlorides? Chloride is the more common one. Of course, bromide can also be used, but chloride is the more common. This can go back, right? This can be converted into anhydrides. This can be converted into esters. This can be converted into amides. I'll go to the rest in a second, but before I do, can you tell me little hard to do. Okay, let it be, don't tell me, I'll tell you.
Remind me, how do you call the ones with double CO?
Say again?
Oh, that's ether, right?
Anhydride.
Anhydride.
And hydrate.
Ether does not have COs.
Oh,
CO.
never mind. Sorry.
Then we can convert this to primary alcohols. It can also be converted into aldehydes. We can convert this into a tertiary alcohol because you've seen it last quarter. But we might also be able to convert it to a ketone. Did I miss any? No, okay. So, where's my red? There. This reaction where acid halide becomes an ester is an esterification reaction because we are making an ester. This is an aminolysis reaction because we are going to use an amine. This is a reduction reaction, complete reduction, whereas this is a partial reduction. And this reaction is a hydrolysis reaction. Those don't have names. Okay? Okay, let's start with one at a time. I think we'll probably spend most time with this family because everything else after that starts following a pattern. So let's start with, where's my cheat sheet? Okay, so a lot of mechanisms for us to write as we go through these. Please tell me. What would I get after those two steps? That's from a previous chapter, so hopefully we can do this fast.
Na2Cr2O7 converts the R group into a carboxylic acid.
So what's the final product, Carter?
An acid chloride.
Do you all agree? Which acid chloride?
What do we which one?
Carboxylic acid. So the OH gets so the C double bond single bond OH. OH gets replaced by a Cl.
But there's no OH. Which
Oh.
OH are you talking about?
Oh, the product from the Na2Cr2.
Could I, sorry to
Cl.
interrupt you, Carter. What is the actual product? The actual final product, anybody?
Could we come up to the board and draw it?
Can you name it?
Oh.
You mean benzoyl chloride.
Benzoyl chloride.
From benzoic acid, absolutely right. Exactly. Here, I'll take it out. Benzoyl chloride. Exactly. Everybody okay?
Yep.
Because that's from the previous chapters. But
Yeah.
now, can someone please tell me? Don't ask me why am I doing this. Whatever. What would be the outcome? Or actually, we don't need heat. Sorry, it is so reactive. We don't need heat at all. It actually can do it at room temperature. Or that. What would we get?
A carboxylic acid.
Good. In this case, which carboxylic acid would that be?
Benzoic acid.
Very good. So hydrolysis of acid halides uses, again, either hydronium or aqueous base. No heat needed because it's extremely reactive. Let's write a mechanism. Let's try and figure out how. I don't need a mechanism for this part, guys. I don't need that, just for the hydrolysis part. So let's do the acid one. Please tell me what will be the first step.
Protonate.
What am I going to protonate?
The oxygen.
Good.
Mm-hmm.
Everybody agrees?
Yes.
Yep.
Because there's an acid, you got to protonate. And the most basic position is the oxygen gets protonated. Okay, good. What would be the next step?
Attack.
What?
Attack,
Attack what? Where?
Where am I? H3O? No, HOH.
Water?
Yeah, water
And where?
attacks into the C double.
The electrophilic carbon.
electrophilic.
Good. Then what?
So we have an OH.
That's your tetrahedral intermediate. Of course, it doesn't have a negative charge because everything is happening in an acidic environment. But what would be the next step?
The oxygen on the OH2 donates
How about proton exchange?
it gets rid of a proton.
And then what?
Don't
Can
we need
I-
a proton exchange
Do a proton exchange from where to where?
from up and down?
From the oxygen to the chlorine.
Oh,
Then what?
I did not.
Then the
Oh, no one cares.
the HCl makes a good leaving group.
Then what?
Okay.
Then what?
The double bonded oxygen donates a proton.
Do you all agree? Everybody okay? Same sequence. Nothing's really different. Right? Protonate, nucleophile attack, tetrahedral, kick out the leaving group because there is a leaving group, and then wherever it takes us. What about the base one? Let's write for the base one. Base hydrolysis. How would that work out? So what would be the first step? Because there is no acid, you can't protonate, you have to do that. Okay, then what?
Then we protonate.
Not here.
Not here.
Because there is a leaving group.
Okay.
If there is a leaving group, once you create your tetrahedral intermediate, what is the tetrahedral intermediate going to do?
Proton.
No.
Kick out the leaving group.
Oxygen kicks out the chlorine.
That is where aldehydes ketones are different from acid derivatives, is because these guys have a leaving group. As soon as you get a negative sign, it kicks out the leaving group.
Oh, so we
But
don't.
then what does it create after that, in this case?
Double.
Since it's still in a basic condition,
So?
it'll be a carboxylate.
So then this can't survive because in the basic conditions,
Oh.
the proton will leave or will be taken and give us carboxylate.
Negative, but then we get the heat.
There's no heat here. You don't
Hydrogen?
really need, but then you can get, I think
Hydrogen?
you'll have to do, you'll have to acidify everything and put the proton.
Uh-huh.
Absolutely right. But do you see the sequence of events? They're exactly the same as before. No difference. Everybody okay? Now the question I want to ask before I go to the rest of them, the question I want to ask is, when you look at the acid halide being hydrolyzed, what was the X substituted by?
An OH.
Good. So what was the nucleophile? In this case, the nucleophile was
OH.
Hydrogen.
H3O plus.
water.
Water.
H2 plus cannot be a nucleophile because it has an H plus in it. Water is the nucleophile. Agreed?
Okay.
What was the nucleophile in this case?
HO.
Minus.
HO minus for the
Everybody
basic.
agrees? Sees that? Okay, because now I want you to tell me. If I want to convert acid halides into an anhydride, what is the X being substituted by?
O.
What is the X being substituted by?
Ester.
OC double bond
By an ester.
OR.
Do you guys agree? Not ester, that's not an ester.
No.
Let's not call it an ester. It is, but you mean this part.
Yeah.
But that's not an ester because there's a C double bond O on the other side.
Yeah.
Ester does not have that.
Well, it's an
But the point is,
anhydride, but
make a prediction. If I want to substitute X by that, what should I use? Make a prediction. You can either use a carboxylic acid, so can I just make it fine so that we can differentiate it? You can either use a carboxylic acid or, notice you used water or hydroxide.
Yep.
So carboxylic acid or
Carboxylate.
carboxylate. Exactly. Exactly. In case of carboxylic acid, protonation will happen first, then nucleophile attack and blah, blah, blah. In case of carboxylate, nucleophile will attack and then blah, blah. Do you guys see that? Everybody. Can you tell me what will we use to convert acid halides into esters? So we are replacing X with OR. Exactly. Alcohols. Exactly. Can
Or-
we use alkoxide? That's a great point. That's a great point on paper. Why not? Because you can do the same thing. Actually, we don't. Just because. Is there anything wrong with it? I don't think so. On paper, no, not necessarily. But alcohol is basically used. Could someone tell me, please, for esterification reaction, what's the byproduct?
RCO.
Louder? HX. What is HX? It's an acid. So how would I do this reaction if I were doing it in the lab upstairs and not make my reaction mixture too acidic? Because HX is going to make it acidic. So how do I do this reaction while keeping this in check so it doesn't become too acidic? Basically neutralize it as it's being created. Exactly. So we'll use a weak base called pyridine, PY. A very weak base. Pyridine is a tertiary amine, by the way. This is pyridine. You will see it in several cases where it's a weak base and its only job is to soak up the HX as it's being produced. It's neutralizing it as it produces, so the pH is not becoming too acidic. Okay, what do you think we should use to convert acid halide into an amine?
Use amines.
Depending on whatever those are, right?
Yeah, use an amine.
So either ammonia, NH3, because then you will get primary amine, or a different kind of an amine, something, because we want at least one hydrogen there, but those can be anything, depending on what you want there. Everybody okay? Now, I don't remember if we've seen this before from last quarter. How do we reduce an acid halide into a primary alcohol? Primary alcohol. Does anybody remember? That's an oxidizer, opposite. Okay.
We're reducing. Oxidizing.
Do you think going from carboxylic acid to primary alcohol, is it a one-stage oxidizing, or excuse me, is it a single-stage reduction or a double-stage reduction?
A double stage?
So then do I need a strong reducing agent or a weak reducing agent?
Strong reducing.
Which one is that?
Okay.
Exactly. But now we are converting, I'll get to that. Well, why not? Let's just do it. But here is a single stage reduction because you're going from a acid halide to an aldehyde. Single stage reduction. Do I need a strong reducing agent or a weak reducing agent?
Weak reducing.
Which one?
NaBH4.
Unfortunately, that doesn't work. I knew that's a good thought that, oh, let's use sodium borohydride, but sodium borohydride
It's just,
actually does not it actually reacts with this. As you've seen in the lab, we have reduced aldehydes to alcohols using sodium borohydride, but I want to keep this. So sodium borohydride does not work. We have a weaker version of La. Stronger than sodium borohydride, but weaker than lithium aluminum hydride, and it is where, by the way, what does La stand for?
Lithium aluminum hydride.
How many hydrides?
4.
So what if we took 3 of those hydrogens away, left only 1 hydrogen on the aluminum? That decreases its reactivity. So the idea is, okay, let's substitute 3 of those H's with something else. That something else is alkoxide, and leave 1 hydrogen behind. It's lithium trialkoxy aluminum hydride. Lithium trialkoxy aluminum hydride, which stops right here. It doesn't go beyond that.
And do we use H2O?
Yeah.
Can we abbreviate it as LAORE?
I haven't seen that. I have unfortunately not seen that anyway. La I see all the time, but
How about
haven't
lot
seen that.
3 and we make it,
But yes, I
A
think
new
this
trend.
one, you don't need a second step though, Carter. This one is weak enough that you can use it in a protic solvent, such as methanol, ethanol, to give us the protons. You don't need a separate step. So, but that gives us partial reduction and stops right here. Everybody
oh, I'm
okay?
sorry, the methoxy is,
No, methanol.
MEOH is methanol.
oh, the methanol,
That's
it's
the
part of
solvent.
the
Yes.
I mean the 3?
It's a solvent.
That,
Together.
how do you call it again?
Lithium,
Lithium.
How do we
aluminum.
call it for short? No,
there's no short.
There's no abbreviated form.
Can
So
we invent
lithium, if you let me finish, lithium trialkoxy aluminum hydride. Yeah, there's no short for that.
let's invent.
Now this one you guys could probably remind me, how are we converting an acid halide into a tertiary alcohol? Notice that 2 of the R's on that are the same.
Excess Grignards.
So we need at least 2 or more equivalents of the Grignard. We've gone over this reaction a lot, right? But then, so that's complete reaction. What about partial reaction, where only 1 R prime gets incorporated and then it stops? So would Grignard work? No, Grignard goes 2 stages, and we've written mechanisms. We'll write those again just to remind
Okay.
everybody. So we need a weaker version of organometallic reagent. We need a weaker organometallic reagent than Grignard. Which one is that?
Gilman's.
Stops right there, doesn't go beyond. Of these all reactions, here are the mechanisms that we need to know. Some of them we should go over, we will go over. Some we have already gone over before. That means everyone should know. We must know this mechanism, we just wrote those. We will go over this mechanism, this one, that one, not that, and this one.
So,
We should.
okay.
Okay?
Acid anhydrides, esters.
It's right there, Carter.
Okay.
Yes. So make a note. Please make a note. Okay? Let's write a few. Hopefully that way we will also start remembering the ones we've already written before. We can also start remembering. Not really necessary. The Grignard one is more important. Please tell me what will be the product. Anybody?
Plus.
So it's an acid halide with a carboxylic acid. What is that going to create?
An acid anhydride.
Good. What is that acid anhydride going to be? So it's this portion with this portion, isn't that right?
Yep.
Oops, sorry, wait, I circled it wrong. This portion, isn't that right? So, what is that going to create?
What the phenol would be.
Benzoic, propanoic, and hydride. Agreed? Let's write a quick. So, what do you think is the role for pyridine?
A base
So, why?
Keep the
to keep the to
Which
neutral-
acid?
chlorine.
hydrochloric acid.
Exactly. There is hydrochloric acid being produced as a byproduct. So that gets absorbed and reacted, neutralizes it, right? The point is, the base is there to neutralize the HCl. Absolutely. Okay, let's write a mechanism. First step, what do you guys think?
No.
Is there an acid in this? Well, there is.
Oh. The oxygen gets protonated.
With what? Where's
Um,
the acid?
in benzoic acid.
Okay, then what?
Then the nucleophile attacks, which is the, benzoate.
Benzoate. Exactly. Benzoate. Carboxylate. Carboxylic acid becomes carboxylate. So benzoate becomes benzoate. Where? Where would the benzoate go?
Bicarbonyl.
Carboxyl. Carbonyl is for aldehydes, ketones, lower oxidation state. Carboxyl is for the higher oxidation. Okay. What does that create? Sorry.
Alcohol.
Not an alcohol. Let's not call it an alcohol, please. What you want to say is this, right? What is that? We don't know a name for that family, but not an alcohol, because alcohol doesn't have all of that stuff attached to it. Okay, what do you think should happen next?
The protons on the oxygen go down, no?
Go down. Which oxygen?
On
Alcohol. So I'm thinking
Oh, the proton goes down.
electrons, I meant.
Go down where?
To the bond, and then later bleeds, but I think.
Oh, you mean not down? You mean up?
Oh, yeah.
they
I just
they
always think of it as going down.
Okay, got it. Kick out the leaving group.
Yeah.
Okay.
Yeah.
And then what?
Oxygen donates a proton.
To who?
Donates a proton.
That's when the pyridine can come in, take a proton. Pyridine, remember, is the weak base, so a strong acid gives a proton. The point is, this is the nucleophile, sorry, circled it wrong again, I'm so sorry. This is the nucleophile that came in and replaced the halogen. Everybody sees that? Everybody okay? Okay, let's try this then. Just tell me what will be the product. Product.
I can write it.
Again,
A
here's your leaving group. What's the nucleophile?
PHCH2O.
So what's the product?
So the Cl is replaced by a
Can we just call it an ester, Carter?
an ester. Okay.
Thank you.
It forms an
Agreed?
ester. Yep.
Once again, what's the purpose of PY? What's the purpose of pyridine?
A base.
Again, why? Because we are creating HCl right there.
We are
So
creating.
the base can neutralize it. Agreed?
Yep.
Everybody see that?
Yes.
Please, let's write a mechanism. Again, look at the similarities. It feels like you're doing the same thing over and over again. What's the first step in this case?
Proton.
There's no acid.
Oh, no acid.
So
Nucleophile.
what's the nucleophile?
The alcohol.
Where would the nucleophile go?
It will
Read.
attack the electrophilic carbon.
What would that create? A tetrahedral intermediate.
Yep.
What will the tetrahedral intermediate do? Kick out the leaving group. What will this do? React with the what?
React with pyridine.
To do what? That's it. Exactly. Everybody okay? But again, please, there has to be a quick way of figuring out the products that doesn't need for you to go over the whole mechanism in your head. The point is we are replacing the leaving group with the nucleophile. What does it create? That should be the pattern we hopefully notice. Okay, let's do another one then. Oh, what are you doing, Sunita? What would be the product?
An amine. An
Amine.
amide.
Amide, which one? Primary, secondary, or tertiary in this case?
A tertiary?
What do you guys think? Do you all agree?
Yes.
So once again, what does that mean? It means this. Which part of this is the actual nucleophile?
The NET2.
Because H and Cl will become HCl, right?
Yes.
So what does that give us? Primary, secondary, or tertiary? Do you all agree?
Yep.
That's what you meant, Carter?
Yep.
Right? Why do you think we need excess of that?
Excess.
Why do you think we are taking excess of the amine in this case? Huh?
Will the initial one?
The initial.
Why do you think we are taking an excess of the amine?
The excess. To react with the acid.
I love the level of enthusiasm. Thank you, Carter, so much. I mean it. Come on, guys. What's the purpose of the amine? What is an amine for organic chemists?
The base.
That's what it is. It is an electron-rich thing. That means it can either act as a nucleophile or act as a base. We are taking an excess because some of it acts as a nucleophile. The rest of it acts as a
Base.
to neutralize. We need that. You guys agree? Please write a mechanism. Go ahead. Take a couple of minutes. Write it on your own. Same pattern. Think about, okay, what should happen first, then what should happen, and so on and so forth.
Nuclear. Come on.
What would you say is the first step?
Nucleophile attacks electrophilic carbon.
And what's the nucleophile though?
NET2.
Is that what you were also saying, Camilla?
Yeah.
Because I heard you said something as well. Good. Then what?
oxygen, the double bond is formed and and the leaving group is kicked out.
Do you all agree? Kick out the leaving group.
Could be a proton exchange.
Not in a basic environment, because it's in a basic environment. So let's kick out Cl minus.
The base take that proton.
Exactly. Which should you show first? That's a good, okay, let me write it, then let's address that. Let me write it and then I'll come to that. And then what? The base will take the proton, right?
Yep.
So the question that I think Jane is asking is, and the base will be the amine, because that's the stronger base than Cl minus, way stronger than the Cl minus, so the base will take the proton. Now, I think Jane is asking which will happen first. Does the base take the proton first and then the leaving group gets kicked out, or the leaving group kicked out first, then the base? Doesn't matter. Show either first and either second, as long as you recognize that, yep, the leaving group is being kicked out and the base is taking a proton from you. Sure, you can show the base taking the proton first and then the leaving group being kicked out, totally okay. Everybody good? Okay, next one, which actually we've done before. Where did my paper go? Oh, there it is. Let's see. Please tell me what will be the product. What will be the product? Anybody?
Primary alcohol.
Which one in this specific case, please?
Benzyl.
Did you say benzylic acid?
Benzyl alcohol.
Oh, sorry, I misheard you. Totally. Benzyl alcohol, everybody agrees? Okay, cool. Let's write a mechanism. What would be the mechanism?
Nucleophilic.
What's the nucleophile?
Law is a source of hydrides.
So the nucleophile is the hydride coming from La. Isn't that right, everybody?
Yep.
So the La gives us a nucleophilic hydride. Okay? What does that create? It creates a tetrahedral intermediate. Agreed? Everyone?
Yep.
What's next?
Oxygen forms, the double bond is formed and the chloride is kicked out.
So what does that create? An aldehyde. Can the aldehyde survive with La?
No.
What is going to happen next?
Oxygen will accept a proton.
Not proton, there's no acid here.
Oh, accept a hydride.
This reacts again. That's why we need 2 or more equivalents of La, because this reaction goes through 2 stages. When it reacts again, this is where it stops, because now it has created an alkoxide ion.
Oh.
Now there is no leaving group to be kicked out, it stops right there. That's the end of step 1. Agreed?
Yep.
And then step 2 comes in because,
Water donates proton.
yeah. The point is that La reacts twice. It reacts once, kicks out a leaving group, creates an aldehyde in this case, which reacts again. That's where it stops. That's why we need 2 or more equivalents of La in this reaction. Does that ring a bell from, I think we did that last quarter.
Last quarter, yeah.
So then a similar one, also done last quarter, looks exactly the same as La. reaction with Grignard reagents. What will be the product? And let's write a mechanism. What do you guys think will be the product?
Two of the R group from the Grignard, and it's a tertiary alcohol.
So the product would be Is this what you mean, Karam?
Yeah.
Everybody agrees? Let's write a mechanism. What's the first step?
Shoot. Grignard attacks the electrophilic carbon.
To make a tetrahedral intermediate.
Tetrahedral. Yes.
Agreed?
Yep.
Then what? What would the tetrahedral intermediate do in this case?
Oxygen would form the double bond and kick out the leaving group.
And this creates what? In this example, what does it become?
A
A ketone.
ketone.
It's exactly the same process if you think about it. That makes an aldehyde because we gave it an H minus. This becomes a ketone because we gave it an R minus. But it's exactly the same process. Okay, but can it survive if there's Grignard around?
No.
So what will this do?
It'll react again.
And what will this do?
Get permeated by the H3O4.
Right, but in step number 1, nothing. This is where step 1 ends. Can't kick out anything. Just like there are no leaving groups anymore, right? So that's when, as Camilla is saying, that's when step number 2 comes in. That's when the first step is finished and now it's ready to be protonated by adding an acid. But please note, guys, the mechanism for La and mechanism for Grignard are exactly the same. The difference is that that's bringing in H minus, this is bringing in R minus. That's the only difference. Everybody agrees? Sure?
Yep.
Cool. Okay, please, let's do this then. Is this okay over there? Feel like you guys are the farthest.
I can erase these for you.
While you erase, I write here, then I'll write there also. How about that? Thank you so much, Mark. I appreciate that.
My pleasure. Everybody okay?
Oh.
Erasing these.
Oh, wait a second. We don't really need a proton. Because once it kicks out the leaving group, it's got the aldehyde and it stops.
So
we
we
don't
just,
really need this. If you look at the.
but we just need a solvent.
Some solvent that keeps everything dissolved, yeah. Oh, thank you, Mark.
You're welcome.
Let me finish, Dash. Come on. Let her finish.
My apologies.
Come on.
I
Just
feel like you
choose
can
the
predict what
easiest
she's
one.
gonna.
Well, I'm waiting now.
Oh, I see.
You
Thank
want me
Yes,
to wait
yes,
now?
yes.
Now
I
it's
did.
I
You almost done yet?
Don't be in a rush. Well, okay, yeah, I'm
This
almost
is 13, so this would be 14. Oh.
Which is the next lab we are doing? Does anybody know? I'm just asking out of curiosity.
Methylsalicylate.
Oh, okay, we are doing that. Okay, good. Thank you. Salicylic. Oh, sorry.
No, you're good.
Is it not maximum?
Oh, can you write excess there? Please, yeah, that, otherwise it's not going to work very well. At least 2 or more we need, otherwise the reaction won't go very well.
Give me a second. Oh, I know what that is.
Once everyone gets the right answers, I'll take a picture of it. Too much to write.
Guys, do you all agree? Let's start from here. Do you all agree? Strong reducing agent gives us primary alcohol because it goes through 2 stages of reaction. Weaker one goes through only 1 stage, so stops at the aldehyde. And then strong organometallic goes through 2 stages of reaction to give us tertiary alcohol. The weaker one stops after 1 stage, so gives us the ketone. Is this okay, everybody?
Yep.
Make sure you can write the mechanism for the first and the third reaction. Second and fourth, we don't have to, but it's the same idea, where H minus attacks, kicks out the leaving group, but then stops after the first stage. Doesn't do anything more beyond that. So please do. Okay, so here we are making an acid halide, and then esterification, hydrolysis, reduction, acid anhydride, Grignard, cuprate, and amide. Everybody okay?
Yeah.
So once again, I think out of these, we should be able to write mechanisms for this one, this one, this one. Yes, why not? Yes, yes. I mean, can you write a mechanism for that? Yeah, you can. I mean, it's just this attacking, kicking out the leaving group, and you're done. But
The
it's
NH
fun.
serves as a nucleophile.
Okay, questions?
Can I take a picture of that?
There, just. Okay, so let's talk about the next family of compounds. Now that you've understood this basic idea, you will notice everything else is exactly the same. Exactly the same. So the next family is acid anhydride, which is the next one in reactivity, acid anhydrides. So how do we make an acid anhydride? By the way, acid anhydrides can either be symmetrical or unsymmetrical, right? Symmetrical if they're the same, unsymmetrical if they're different. How do we make them? Well, one way to make them is from the carboxylic acid. How? We can react it with basically another carboxylic acid.
Or carboxylate.
And carboxylate won't work because carboxylate might just deprotonate that because that's an acid and carboxylate can be a base. So it won't really work that well. The best thing is to do an intramolecular, excuse me, I said it wrong. The best way to do it is do an intermolecular dehydration reaction. So there's a H2O that's taken out, but it's being done intermolecularly rather instead of intra. Now this method is best for symmetrical ones only. This method is the best one when R's are the same, because otherwise you get three different products, and then who wants to deal with that? So this is, again, please make a note, best if R's are the same. But then we can also make it from the family that's more reactive than itself. Which one is that?
Acid halides.
What would we use to convert an acid chloride or halide into an anhydride? Once again, you can either use an acid with a weak base pyridine, or you can also use a carboxylate. But where do we get this from? This comes from
SOCl2.
Everybody okay? So I know I'm running out of time, so how about I ask you to do this at home? Please tell me what will be the outcomes. I don't have space. What should I use to convert this back? What would I get if I reacted this with alcohol? What would I get if I reacted this with an amine? What would I get if I reacted this with Na? What would I get if I reacted this with same things? How about and so please complete the rest and tell me what would I get when I do those reactions, starting with the anhydride. Again, the hint is the same thing that you saw. Everything is going to be the same from now on for different families. So please try this out. I would also ask everybody to practice. Can you write this mechanism? Can you write this mechanism? How about this one? How about this one? And how about this one?
So,
So on Monday, please, at the very least, tell me what would those create, and make sure you know how to write those mechanisms. After that, we'll go on to esters.
Do we have a quiz on Monday?
Yes, we do have a quiz on Monday. Oh, I forgot. We do have a quiz on Monday. So what will the quiz on Monday cover? Let's just cover it through acid halides.
okay.
Let's cover it through acid halides, not the anhydrides. Is that okay?
Yes.
Oh, today's Wednesday. Okay. Forgot.
Anything for the lab? I don't know.
What do you mean?
Like any comments for the lab?
The one we
one?
did yesterday?
No,
or
the
the
next
one
one.
that next week?
Yeah.
No. I was just asking because the ester, because we're making an ester. So the reaction is something we look at on Monday.
See you.
Do you want to meet up tomorrow? to
Yeah,
study?
tomorrow we're gonna meet up.
Tomorrow